Okay, so I'm just going to work through the multiple choice questions on the review. So starting with the first one, selected values of the function g are given in the table above. Which of the following statements is true, about g is most appropriate? So it's all about whether or not g is linear or exponential. So when you look at how the output values are changing, it looks like they are all increasing by 4. So, because they're all increasing by 4, it's definitely linear. So then we want to make sure we choose the right statement. So G could be linear because over equal length input value intervals, which is true, they're all increasing by 1 here. The output values change at a constant rate. Yes, and that rate that they are changing is 4. All right, and then B says that it's linear, which is true, but it's saying that the output values change linearly as the input values change proportionally. No way, Jose, that is true. All right, so let's look at number 2. So kind of the same situation. We have H, and we want to find what is most appropriate. And as you're looking at H, you can tell that you are multiplying by 3 each time to get the next output value. And so that means we're going to be exponential. So then we have to choose which choice is true. And so C says that we have equal length input value intervals, which is true, and the output values are changing proportionally. That's what we say whenever we're multiplying by something. All right. And then number 3, we have a table of values. It tells us it's an exponential function. It also tells us the base form of it, a times b to the x, where a and b are both positive constants. And we want to know what's true. Well, it tells you that a and b are positive, so a is greater than 0. A is actually 16 in this question. We don't technically need it to answer the question. What we need to figure out if we're doing growth or decay, and then the reason why it is that. So we can do that by finding b by taking one term and dividing the previous term from it, which is going to be 1/4. And so this is going to be decay because a is greater than 0 and b is between 0 and 1. Now, if we were multiplying by something between or greater than 1, then it would be exponential growth, if that was the case, but it's not. All right, let's look at the next one. We have this function g. We want to know which of the following pairs of limit statements describes the behavior of g. So I am going to go kind of down in this corner, and I'm going to just draw something that you might need throughout the review and throughout the test. So I'm going to have like 4 little sections where we have a graph. We have a graph in each section. And these are going to be exponential graphs based on the values of a and b. Okay, so when a is positive, it's going to be graphed above the x-axis and it's going to be concave up. And to decide about growth or decay, you look at the value of b. So if b is between 0 and 1, that's going to be exponential decay. So concave up, and it's going to be decreasing. Okay, a is greater than 0 and b is greater than 1. That's exponential growth. It's graphed above the x-axis and it is concave up. Okay, and then when a is less than 0, it's not considered exponential growth or decay. It's still an exponential function, but it is going to be below the x-axis. The graph is going to be concave down. And so it's going to be a reflection of one of the growth or decay graphs. So if b is between 0 and 1, it's going to be the reflection of this graph here across the x-axis. So it's going to look like that. So I used to call that reflected decay. All right, and then this one, a is less than 0 and b is greater than 1. It's going to be reflected exponential growth. All right, so you might need that throughout the review, throughout the test, so that's just something to keep in your brain. So whenever we are looking at 4, a is greater than 0, so it's going to be graphed above the x-axis because a is 2 here. And then b is 1/3, so 1/3 falls in between 0 and 1, so this is going to be an example of exponential decay. All right, and then the limit statement, so the x approaches negative infinity is the left side. So we're looking at the left side is pointing upward, going towards positive infinity. We only have one that does that. And then the right side is flattening out at 0, so this answer should be B. All right, number 5. The function h is an exponential function that is decreasing at a decreasing rate. Try to remember what that means about concavity. So decreasing rate means the rate of change is decreasing, and that means the function is concave down. So decreasing rate automatically means concave down. So the whole function is decreasing, and there's a decreasing rate. It's going to look like this one right here. So it's going to be falling and concave down. All right, and all that stuff happens below the x-axis. So on the left side, it looks like we are going towards 0. And then on the right side, we're falling, going towards negative infinity. Okay, and then number 6, we have another exponential function. A is positive, so I know it's graphed above the x-axis. I also know it's concave up if it's going to be graphed above the x-axis for exponential functions. We also know that the base is greater than 1, so we have concave up, we have exponential growth, and we have increasing, so that is A. So this one right here falls in this section right here. So A is greater than 0 because it's positive, and B is greater than 1. All right, number 7, the figure shows the graph of exponential growth function f. The coordinates of 2 points are labeled. We want to know the y-coordinate of the point where x is 0. So we actually need to go backwards twice. And so if we're moving backwards to get from one point to the next, the x-coordinate is just going down by 1. But the y-coordinate is getting multiplied by 1/2 or divided by 2. And so we'll do that again and get 6. And then one more time and get 3. So you can think of multiplying by 1/2 as we go backwards, or dividing by 2, however you want to think about it. Right, and then you can just double check moving forward. We're multiplying by 2, so 2 times 3 is 6, times 2 is 12, times 2 is 24. All right, number 8 says that at time t equals 0, the value of a truck was $65,230. During the next 10 years, the value decreased by 15%. Okay, so decreasing is depreciation, and so you are going to subtract that 15% from 1, or 0.15 from 1, because it's a decrease. If by chance the one on your test is increased by, you would definitely add it. All right, and so we want to know which one of these corresponds with that. So A is going to be this initial value, and then we need to do 1 minus 0.5. And 1 minus 0.5 is going to be 0.85. So it should be C. All right, number 9, we have this decreasing function L. Gives the number of leaves in Mr. Parsley's yard in thousands over a period of 4 days. He began raking on day 1. If the model is constructed to represent these data, which of the following would best represent the situation? And so you can kind of tell, like, as you go through from one point to the next, definitely decreasing proportionally. So we're going to have to, well, if you decide that, then it's obvious that it's going to have to be C, because if these values are getting smaller, you're going to need to be multiplying by a number that is smaller than 1. So this would be growth, and this one would be decay. If there's 2 that end up being decay, you can just double check what you're multiplying by taking a term like 48 and dividing it by the previous term. And then you would need to reduce both of those. And let's see, they reduced by 8, but that's not going to be the biggest thing that they reduced by. So I guess 16. 16 is the biggest number they reduced by. That might be a little difficult to do in your head, but this is non-calculator, so you can reduce a little bit at a time until you get to where it's fully reduced, and that's going to be choice C. So 64 is there because that is the initial value at day 0. So it looks like we're multiplying by 3/4 each time. Okay, and then number 10, a regression model S is constructed for a data set. The residuals from the regression are plotted and labeled based on the vertical axis of the residual plot, which is not shown. Point A is located at -0.7 and point B is located at 2.9. So if you wanted to draw a residual plot and label those, you can. I don't really think it's necessary to answer this question, but you can. So -1.7 would be about right here, and positive 2.9 we'll say is about up there. Okay, and that gives you, those are residuals, and residuals were found by taking the actual value, like from the data, and subtracting what the model gave you, the predicted. Sorry, I can spell predicted, I'm pretty sure. The predicted from the model. And so what happened to get the -1.7 is they did the actual minus the predicted and got a negative. So if you subtract actual minus the predicted, it means that the predicted was larger. Because you subtracted and got a negative, the predicted was larger, then it was an overestimate. All right, and then for B, they did actual minus predicted, and they got 2.9, which means the predicted was smaller. You subtracted and got a positive. And so that means that predicted value was an underestimate. And it underestimated by a larger amount. So it was 2.9 off. This one was only 1.7 off. So you need that to answer the question. And so part A says that the model produces an overestimate for A, which is true, and an underestimate for B, which is true. And based on the absolute value of the residuals, the error was greater in the model with B than with A, because it has a larger absolute value. That's absolutely true. So if you don't want to memorize that a negative residual means overestimate and a positive means under, then you just really need to know this. and then just kind of logic your way through it. So if you subtract and get a negative, that means the predicted was bigger. If you subtract and get a positive, it means the actual was bigger. Okay, here are a couple more residual questions. And so on 11, the exponential regression was used to develop a model for a given set of data. The figure above shows the graph of the residuals of the exponential regression. Which of the following statements about the exponential regression was true? So we did an exponential regression, and this is what we got. So you have to figure out, was this appropriate? This is the residual graph. If the residual graph shows a pattern, like this is a clear pattern, this is not appropriate. Okay, and then it goes through like it was appropriate because there's a pattern, it was not appropriate because there was like different things. The truth is, the exponential model is not appropriate because there is a clear pattern in the residuals. Okay, so again, more residuals. Without even reading the question, when I look at these residuals, I can see that this is a pattern, this is a pattern, this is not. So what you want to see with residuals is alternating above below the x-axis, which is what this has. So I haven't read the question yet, but I know this one was the appropriate one. And both of these are not appropriate. So let's see what it says. All right, a set of data was used to create an exponential, quadratic, and linear model. The residual plots for the three models are shown above. One is exponential. That's all I probably need to know to answer this. B was the residual from a quadratic. And not B, 2. And then 3 is the residual from a linear model. So the exponential model is appropriate. And then we look here and see what exponential choice, which is the exponential choice, which is D. D is the exponential model. So it's exponential, so then you pick which model represents an exponential. Okay, let's look at number 2. I'm sorry, let's look at number 13. All right, the function is given by this quadratic function, x squared minus 2, that's f. G is 3 minus x, and we want to find f of g of x. All right, so f of 3x minus 4. So everything that I put into f, I'm going to square it and then subtract 2 from it. Now you have to be careful when you square 3x minus 4. You can either multiply it by itself, which is perfectly acceptable. So you would have to distribute the 3x. And then you would distribute the negative 4. And then finally, you would combine your like terms. So you would have to combine the negative 12x minus 12x, which is that. And then you would have to combine 16 minus 2, which is going to be 14. So it's choice A. Now, if you would rather, you can use a shortcut that I like to use, but you don't have to. So when you use this shortcut, you square this first one. When you square 3 and x, you get 9x squared. And then you multiply these together and get negative 12x, and then multiply by 2. That gives you your negative 24x. And then when you square negative 4, you get the 16, and then just make sure you subtract 2 from that 16. All right, number 14, we have a table of values for f and g, selected values of x. Functions f and g are defined for all real numbers. And there's this new function h that is f of g of x. So if we want h of -2, we want f of g of -2. So we're going to start with g of -2. This is just regular compositions, nothing weird. So we go to where x is -2, g is 2. So it gets replaced with 2. And then to do f of 2, we go to where x is 2, f is -2. Okay, for number 15, we have the function c models the temperature in degrees Celsius as a function of time. So c as a function of time would be c of t. All right, and then we have this other model, P, which is pressure, and P, it gives pressure as a function of temperature in Celsius, so it would be like P of C. And then we're going to do a new function, K, that is P of C of T. So basically what happens is we take this and put it in for that C, and the C gets dissolved, and you're just left with pressure as a function of time. And so that's going to be choice B. All right, number 16, we're going to find the inverse of this function. So to find inverses, the first thing you do is you switch x and y. And then you're going to solve for y by multiplying by the denominator. So you multiply x by y minus 2. So I'm going to go ahead and distribute it. All right. Then anything that has a y, we're going to move over to the left side. Anything that doesn't have a y, we're going to move over to the right side. All right. Then we're going to factor out a y. And then finally, we're going to divide by what's being multiplied by y, and that should be our inverse function. All right, and then number 17 is a composition involving inverses, so it is a little bit more difficult. So we're going to do h inverse of k of 1. So starting with k of 1, just the x is 1. What's the value of k? That's going to be 2. All right, h inverse of 2 means what x is going to make h equal to 2. So we're looking for this. What x makes h equal to 2 is going to be 3. So when you're solving an inverse, you're looking for an x that gives you that y value. Okay, and then on 18, we have this piecewise linear function. G is the inverse of f. So this is, doesn't tell you. This should be labeled as f. All right, and so we want to find the maximum value of g. That's the maximum y value of g, and it should match up with the maximum x value of f, which is going to be 8. Because the inverses, the x and the y's are going to switch. Okay, and then this one starts the calculator part. So let me pull up a calculator real quick. All right, so the table above presents values for a function g. An exponential regression AB is used to model this data, and then we want to find g of 3.5. All right, I'm just clearing some stuff out. Okay, so what we're going to do is go ahead and put that data into the calculator by hitting stat and then edit. And then I have some stuff in here I'm just going to clear out real quick by just hitting up, clear, enter. All right, and then we're going to go ahead and, since it said it's exponential regression, we'll choose exponential regression by going over to calc and then choosing choice 0. And I am definitely going to store it in Y1 because I have to use it in a second. Okay, and then once I have that stored in Y1, I can just do Y1 of 3.5. Oh, sorry. And there it is. Looks like it's going to be choice B. And then for number 20, we have a new table. And the function APPC gives the total number of Android users worldwide in billions from 2012 to 2017. A quadratic regression is used to model APPC. What is the residual and the number of Android users in billions? Okay, we have a lot to do on this one. The first thing we're going to do is put this data in the calculator. All right, and then it tells you they did a quadratic regression, so let's go ahead and do that. And definitely store it. Okay, and so just another reminder that you're gonna have to remember that the residual equals the actual minus the predicted. Now, I keep saying that, and some people still, they know that, but then they can't remember what the actual is. The actual is the data. That's the table. The predicted comes from the model that we just get, the regression model. All right, so we want the residual when t is 4. So the actual when t is 4 is 1.7. All right, and then the predicted, I would just, since I stored that in y1, I'm just going to do y1 of 4. So that's the actual from the data minus the predicted from the model when x is 4, t or whatever. So that's what it is, and that's going to be choice B. All right, and then number 21. In a certain simulation, the population of fruit flies can be modeled by a geometric sequence where the first day of simulation is day 1. The population on day 3 was 200 fruit flies, and the population on day 7 was 450 fruit flies. What is the population of fruit flies based on day 5, or on day 5 based on this simulation? So we can actually do regression on this. So a geometric sequence is going to pretty much correspond to exponential regression. Now the difference is an exponential regression equation is going to be connected. The geometric sequence is just going to be a sequence of points. It really doesn't matter for what we have to do. It's going to be fine. So you're just going to go ahead and do a table of values. You're going to do list 1, list 2, where list 1 is the day, and list 2 is the number of fruit flies. Alright, so it's going to be stat edit again. We're going to clear out again. And then just put in our 2 data points. Alright, and then we're going to go to exponential regression. I went the long way around. Alright, we want to store it again because we are going to use it. And what are we trying to, we want to find day 5. So that's going to be, y1 of 5, which is 300 fruit flies. All right, so that's the multiple choice. So be ready for your test, multiple choice test.